Corporate finance practice problem in OneNote. Present value with planning scenarios. Scenarios that will include calculations for the present value of annuities as well as present value of one. Don't leave profits solely to chance. Instead, use corporate finance. Here we are in OneNote. If you have access to OneNote and would like to follow along, you're not required to, but if you have access and would like to, we're in the tab up top here. We're in the practice problems and we're down here in the 920 present value planning scenario section. Also note that if you have access to OneNote, you might want to use the tool of the immersive reader. That gives the option of actually hearing the text when there's text files within it. It can also convert to Spanish, and you can also then listen to it in Spanish, although it's going to have the translations from text to Spanish, so it's a couple translations, but might be useful. We have that information oftentimes with the transcripts that would be down here related to these presentations. So if you have a transcript down here for the text for the practice problems right there, and the same one for the 920, you might be able to get a transcript and then be able to translate it and possibly hear it in multiple languages. All right, closing this back out. Then we're going to have our information up top. We'll go through that information in the blue area down below. Here's going to be our scenario to start with. How much must you invest to get $15,000 in the future 9 years from now? So our question, lump sum that we're going to put in at this point in time, if it was to grow, then how much would we have to put in now at this one point in order to, in 9 years, get $15,000? We'll do this. This is a present value of one type of calculation. We'll do a similar type of calculation with an annuity, meaning how much might we have to invest each year to build up to a certain amount, and that'll be in the second half of our practice problem here. First off, just note this could be a little bit confusing to just think about the fact that this is a present value type of calculation because we're thinking about how much we'd have to put in now to get to some point in the future. And you might start thinking, well, maybe I should do that by basically just picking amounts that I would put in right now and then do a future value calculation, which you could do, but that would be a trial and error type of scenario. It would be faster to say, okay, if my goal is to get to $15,000 in 9 years, then I want to take that $15,000 and present value it, bring it back to the current period, and that's how much I would have to put in today in one lump sum for it to grow to the future value. So those two calculations are related, of course, present value and future value. So that's how we'll be pulling this back. Then that's 9 years out into the future, so that's going to be our periods, and then the rate is what we would have to decide. We'd have to say, well, what rate do we think it will be? We'd have to pick that out using inflation and possibly using what the alternative for money would be, which would be the opportunity cost of money. What else could we do with it if we had it today? How much could we get in terms of gains on it or investments in it? So we have our formula down below. We're going to break this formula out. Present value equals future value times 1 over 1 plus R. I'm going to break that out into a table type of format here. We have this in Excel too. If you want to check it out in Excel, you can look at it there as well. Future value, we're going to pull that out to the outside. So this is where we expect to be. That's going to be the future value, basically the numerator. And then we're going to have 1 plus R to the n. So 1 plus R to the n. And do the calculation. There's the 1. The R is going to be the 12%. 1 plus 12% is 112%. Note that if you're putting this into a calculator, be careful that you're dealing with rounding and you're dealing with percentages. So make sure, are you looking at it in terms of a percent, which would be 0.112, which would be 112%, or a decimal, which would be the 1.12 on the decimal. We're taking that then to the n. That's going to be the n, the number of periods. In our case, where our periods are years, and we have 9 of them. So we're going to take that to n. So that's going to be the 112% to the power of 9, caret 9. So we're going to take that out, and that's going to give us about, if we round it, 2.77308. Remember, there is rounding that's going to be involved in these, and you got to take those into consideration. If you're doing test questions, make sure that you're following the directions as to how far out they ask you to round. Then the present value is going to be this 15,000 divided by the 2.77308. That's going to give us the 540915. So 540915, then that means that we would take the 540915 is how much we would have to invest today if we had the rate at 12% and in then 9 years to get to that 15,000. So that's going to be the first way we can calculate it. if we take this amount, this 540915 divided by 15,000, that's how we can basically construct the tables, and we'll do the same calculation in terms of the tables shortly. So down here we have Excel. If you do this in Excel, you could populate this in Excel. We will work through this in Excel with our present value calculation, similar to a financial calculator type of situation where you would take the rate, which would be the 12%, and then the second cell that we would pick up is the number of periods, in this case 9. Note that we're talking about years here. We're not talking about months, and therefore just make sure you got the correct period there. And then we're not putting anything in for the payments here because the payments are used for an annuity, and this is present value of 1. And then the future value is going to be the 15,000. That once again would give us that answer of 5,409.15 much easier. Then we're going to go down and take a look at the tables often used for like book problems. Make sure you're picking up the correct table. This is not an annuity, but present value of 1. Therefore, these numbers, you would expect them to be less than 1 in the table because really you're taking some number in the future, bringing it back. So you would multiply it by something less than 1. If it was an annuity table, you would consider or believe or think that you would be multiplying it times something more than 1, considering the fact that you're taking that payment, which will be reoccurring over time. So we're going to do the table time here at the 12%, 9 years or 9 periods. So is that right? 12%, 9 periods, 12%, 9 periods is going to be down here, 12 and 9, 0.3606. So there's the 0.3606 multiplying the 15,000 times the 0.3606 gives us that 5409, slightly different than what we got here because the tables are rounded to 4 digits. Remember that we calculated it at 0.360610 and so on, and it is rounded down here. Be careful of the rounding with test questions. Let's take a look at another one. This is going to be a present value of 1. Then we'll get to the annuities. We'll do this one a little bit more quickly. So we're going to say, what if I want to get to 20,000 in 17 years, and we have a rate that we're assuming to be 7%. So once again, we're going to basically take that 20,000 where we want to be at in 20 years, and then bring it back to the current period. That then would be the lump sum that we would have to put in today for it to grow at that rate to get to the 20,000 in 17 years. You can also think about this and say, what if I just start using the future value calculation and I just start guessing numbers and see how close it'll get to the 20,000? You could do that, and you could use a goal seek in Excel to do that as well, but it would be faster if you want to get an exact number to do it in the reverse format. Take your objective, 20,000 in the future, bring it back, present value it to the current point. That's how much you would have to put in a lump sum to get there. Once again, future value times or over 1 plus r to the n. Future value is going to be the 20,000. That's our goal. The rate, 7%. The number of periods, 17 in years, not months. So we're going to say the future value is going to be that 20,000. That's going to be on the outside that I'm going to be putting. And then internally, we're going to take the 1 plus r to the n. That's this calculation, 1 plus r to the n. Basically making like a tax type of format, a table format of this algebraic calculation. And then the 1 plus 7%, be careful that you're talking about percents and decimals here. So 1 you can represent as 100%, right? Plus 7% would be 107%. Or 1 plus 7% would be 0.07 plus 1 would be 1.07. And then if we then take that to the power of the number of periods, that's n, which is 17, that would then give us this amount rounded. So we're taking the 107% to the power of or caret of 17, giving us approximately this number. Be careful of rounding. And then the present value would then be the 20,000 divided by that, and that's going to give us the 6331.49. So that would mean that if we put a lump sum in today, 6331.49 at the 17%, after 17 years, we'd hit our goal. Hopefully, that's our calculation of the 20,000. You could test that out by looking at the future value calculation if you so choose. Then we're going to go down and take a look at that in an Excel calculation. We do this in Excel if you want to take a look at that. And it would be a nice quicker calculation, present value calculation. Same present value calculation used for both an annuity and present value of 1, although slightly different component. What will be different? The rate is going to be pulled in the rate. Then they got the number of the periods. The number of periods would be 17 in years here. This is where the difference would be. The payment, we're not talking payments because that's an annuity term. That's why it's going to be 0. And instead, we use the future value of the 20,000. That would give us that same number. Let's take a look at it in terms of the table time. Same thing, table time now. 17 and 7%, so 7%, 17 years. So there's the 7%. 17 years would be down here at the 0.3166. So there's the 0.3166, 20,000 times the 0.3166 gives us the 6332. Slightly different than the same calculation we did up here because the tables are rounded to 4 digits. If we were to take the table out more than 4 digits, we could see that we came to here 0.31657 by taking this amount divided by the 20,000. That's how you can construct the table. 0.31657 is rounded down here to 0.3166. Let's take a look at an annuity type of scenario now. So how much must you invest to get each period 8,000 for 15 years at 11%? So now we're saying I would like to put in a lump sum at this point in time and get paid a fixed amount, 8,000 per year for some period of time, 15 years. So how much would we have to put in today to basically do that? So what we want to do then is present value the annuity payments here. So now we got a number of payments. We want to present value the annuity, bring this series of payments back into simply the current day, and that's going to be how we basically come to that calculation. So let's take a look at that. We'll do that a couple different ways, once again with a formula up top, and then we'll take a look at it in terms of tables as well. So we'll do this in terms of a formula. It'll be a little bit more complex. I'm going to put the C on the outer column here. So that's going to be basically the payment. It's going to be on the outer column. And then we're going to have the numerator and denominator that we're going to pull into the inner column. And then we'll have an inner column for some of this business up top on the numerator where we have a lot more detail going on. So we're going to break this algebra out step by step into basically a table type of format. So we've got the 8,000. That's going to be the amount of the payments, the amount that we're going to receive or that we want each period, which is each year. Then I'm going to look at the numerator, which is going to be 1 minus all this stuff. I'm going to start with 1 up top. Then in the inside, we're going to pull in the 1 plus r to the negative n. That's what we're going to figure here. 1 plus r to the negative n. We get the answer to that, and then we'll take 1 minus that answer. So it's going to be 1 plus the rate, 11%. Remember, be careful with the percents and decimals. So 100% plus 11%, or 1 plus 0.11 gives you 111%. And then we're going to take that to the number of periods, negative number of periods, which is 15. So 111% to the 15, caret 15, is going to give us about 20.90. So take into consideration rounding here as you're thinking about these calculations. And notice this is being worked in Excel, so we're actually using the actual numbers when we do these calculations, even though, we're taking it out to how many decimal places are here, but Excel will have the actual number. So be careful with the rounding. So then we're going to be taking the 1 minus that amount. So 1 minus this amount, that's going to give us about the 79.10%. And then we have the numerator now. That's the entire numerator. We're going to divide that by the denominator, which is once again the rate, and that's going to be the 11%. So the 79.1 divided by 11 is about then this 7.19. Be careful on how you represent these percents or non-percent items here. And then we're going to take that and multiply it times the 8,000. That's going to give us our 57,526.96. So there's our 57. And notice this rate here is actually this if we pulled it out to more decimals. And this is what you would expect to see on a table. So that means if we had the 57,526.96, then you would think that that would be equivalent to the annuity for the 8,000 for 15 years, and that would be hopefully enough to then at the 11% receive then the 8,000 for the 15-year period. So that's a fairly long calculation. We can also see that calculation down here with if you used Excel or financial calculator much more quickly. In Excel, it would be looking something like this. We'd use the same PV type of calculation, present value calculation. We would take the rate which would be then that 11%, comma, the number of periods, 15 once again, then comma. Now we're going to be using the payments because this is going to be an annuity calculation, and we're talking a payment each time. That's going to be the 8,000, and then we don't need the future value, not using it this time. That's why we can use the same present value for an annuity or present value of 1 with that distinction, that difference. There's the 57,526.96 again. Then we can also do this with the use of the tables, making sure that we're picking up the proper table, this time the annuity table, as opposed to the present value of 1. So we have our 8,000. Now we would expect this number down here not to be less than 1, but greater than 1 from the table. And we're looking for the 15 and 11%. Let's go to the table time. Table time, annuity time, 11%, 15 periods. That's going to be the 7.1909. So there's the 7.1909 times the 8,000. There is, once again, the 57,527.20. That 57,527.20 may be slightly different than the 57,526.96 because of rounding on the table to 4 digits. Note that we calculated up top that it would be about 7.190878, which they then rounded to 1.1909. Let's do it one more time. This is another problem for an annuity type of calculation. How much must you invest to get each period the amount of 60,000 for 35 years if we assume the rate to be 10%? So now we're going to say, okay, how much would I have to put in today in order for 35 years to get 60,000, and then we're using the rate, the discount rate of the 10%. So we're going to do that with a formula. Once again, this is an annuity type of calculation, basically present valuing the annuity, this series of payments, which will give us the lump sum that we would have to put in today in order to receive that basically annuity kind of calculation. So we got C times the 1 minus 1 plus I or R interest to the negative n divided by I. I'm going to put these two items on the outer column of our table. We're making basically kind of like a tax return type of format here that will break this algebraic problem into. So we got C in the outer column, and then we're going to pull into the inner column this 1 minus this top portion. We're going to break out the numerator into some more nuance of the numerator. So we're going to say 1 and then minus the 1 plus I to the negative n, which is this portion, 1 plus I to the negative n. There's the 1. There's the rate, 10%. Be careful of the decimals and percentages, 100% plus 10%, or 1 plus 0.1, 110%, or 1.10. And then we're going to take that to the power of n, negative n, which is the number of periods, or 35. So 110%. Caret, or to the power of 35, gives us about, take into consideration rounding, this is in Excel, therefore the actual number is being used even though it's rounded to 3.56. Then if we take that 1 minus the 3.56, that being the numerator, giving us the entire numerator, that being at the 96.44 about. So now we have the numerator. Now let's take a look at the denominator, which is I, or the rate, or R rate, 10%. So we'll take then that 10%. And now we got the numerator and the denominator as one numbers. So when we do that, then we divide them. So now we're taking the 96.44 divided by the 10%, gives us about 9.64 about. Note, be careful of the decimals and whatnot, converting from decimals to percents. And then we've got the 60,000 here times this 9.64, which gives us the 578,649.54. Note that if I divide this out, that amount that we have on the table would be 9.644159, which is basically this number, which is rounded to 2 digits. If I took it out to this many digits, that's how many digits we can look at, and we'll compare that to the table that we'll see later. So in other words, we would have to put in 578,649.54 in order to get 60,000 a year at the 10% discount rate for the 35 years. Let's do that with an Excel calculation. If you were to put this in Excel, and we do have the Excel problem if you want to practice that one, highly recommend it. We would say, all right, well then that would mean that the rate here would be the rate of the 10%, and then comma, and we would take the number of periods, 35, comma, and then because this is an annuity formula, we would be picking up the payment amount of the 60,000, and then nothing's in the future value because that would be used for the present value of 1 instead of an annuity. That once again gives us the 578,649.54, which is the amount we'd have to put in a lump sum now in order to get the $60,000 a year if we have the rate at the 35% for the 35 years. Let's do it with the tables. Table time, same thing with the table time. 60,000, we're going to look up on the annuity table, making sure that we're picking up the correct table, not the table of one, but the present value annuity table this time. And we're looking at the 35 and 10%. So 10%, 35, got the right table. So 10%, 35 years, that's going to be the 9.6442. So there's the 9.6442 from the table. 60,000 times the 9.6442 gives us once again pretty much the same, close to the same, 578,652. Why isn't it exact though? Because this is rounded to 4 digits this time, and up top we used basically Excel to calculate it, which took the full number even if we did round it. So notice, even if we're showing a number less than 4 digits, we actually used the full number because we used Excel. So be careful with that rounding. Get used to Excel. Highly recommend using a spreadsheet. When you do so, you got to be careful of decimals, percents, rounding. That's always the case. So we got the 578,652. This 9.6442 is close to what we had up top here. We calculated it if we took it out to more than 4 decimals, 9.644159. Note that in this problem, we actually only rounded it here to 9.64, but this was actually done in Excel. So really, we're using the whole number in Excel. And so that's what this number is going to be, the exact number, even though it's only showing the 9.64. And once again, get used to Excel, get used to electronic spreadsheets. Know that concept because in practice, it's useful. So 9.644159, and we have the 9.6442 rounded to 4 digits, resulting in this 578,652 being slightly different than the 578,649. Also note that when you're talking about bigger numbers here, it's possible that rounding even 4 digits out might be slightly different. That will not be a problem normally for normal decision-making purposes. It will be immaterial for normal decision-making purposes. However, book problems can take advantage of that. Test questions can take advantage of that to force you to use one method or the other with regards to the multiple choice questions, which will simply differ by this immaterial amount, but which can distinguish the method that has been used to calculate it.